Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And also, we have a free MSE Company Database categorized by industry sector, location, as well as internship and full-time titles. So if you're interested in that, you can find the link in the description below. So today's episode is focused on biomimicry and helicoid composites. So David and I are currently looking up other examples of biomimicry, and it's actually pretty fascinating. David, you had a pretty cool one. You want to talk about it?
Yeah, so I recently just found an article that robots are basically using a snake-like skin to be able to crawl. So I'm not exactly sure the applications of this, but I think it's just pretty cool that looking at nature, we can try to replicate it into things and understand why things work like they do. And so in this article, they use different types of like patterns of the snakeskin, and it results in different methods of travel, like how fast and how much grip and things like that. And so of course, like all this just like leads to further knowledge of like how we can actually utilize this in industry. But I just think it's pretty cool. What have you found?
Well, quick question then. Does it say like, is it specifically the patterns of the snakeskin, or is it like a similar material as well? Does it say it in whatever article you're looking at?
Yeah, it seems like it's just pattern, particularly. They're using different like geometric patterns, like circles, prisms, and then like rhombuses. And it results in different methods of travel. So potentially like tires or other things could use this knowledge to give better grip would be my first idea. But
yeah, you were saying robots, right? The first thing that came to mind was like a Mars rover. Maybe if it's like more efficient in terms of just how it crosses terrain. So that's the only thing
around on Mars.
It's just like wiggling. I don't know. Maybe if it's more efficient, they'll do it. But
cool. Okay, what did you find?
Yeah, I found bullet trains inspired by kingfisher birds. So I guess so in Japan, daunting task of creating these high-speed bullet trains. And so what I'm seeing here is as trains enter tunnels, vehicles would create like a loud shockwave known as a tunnel boom. And so the power of those shockwaves would sometimes even cause like damage to tunnels. And so I guess it says here, the design team, the culprit, the root cause was the blunt front nose cap of the train. And so to minimize the tunnel boom and increase kind of the aerodynamics of it all, they modeled it after the beak of the kingfisher bird. And so I guess it says here they have kingfisher birds have specialized beaks, allowing them to dive into water to hunt while making a minimal splash. And so they modeled it after the kingfisher bird's beak, and the next train was 10% faster and consumed 15% less electricity. So
wow.
Yeah, and then it says here in this article, it's a digitaltrends.com article. So full credit to them. They said most importantly, no more boom. So but yeah, it's fascinating seeing all of the potential like biomimicry examples and how to convert them into engineering. I saw shark skin, but David called that lame, so we won't talk about it.
I don't think it's lame. I just think it's the one that's most common and you always think about. So I want to give the listener something new.
Yeah, for sure. And so one thing that's super fascinating in this episode is the Mantis Shrimp. They have some internal architecture that resembles like a helicoid structure. You'll have to tune into the episode to kind of learn about how that structure is found in nature and how that converts to kind of potential applications in EVs and even hockey sticks. So really fascinating stuff. What was your favorite part, David, that you think everyone should listen to or look forward to?
Yeah, so I think a big trend in recent industry is the simplification of parts. And so Tesla made the Gigapress, turning like 168 unique into two frames that get pressed together to make one final car. And so when we talk about additive manufacturing and other ways of simplifying these parts, one thing that we don't think about is how does crack propagation work? And so now if one part gets ruined, instead of replacing just a really small part, you have to replace the entire car. And so our guest goes into how helicoids can help reduce this. And it's very interesting overall and kind of shifts the perspective of like, oh, like I thought this was great with no downsides, but now we bring up new issues that we've created by trying to solve old issues. And so you have to listen to see the solutions to that and what we can do to allow the benefits to shine through without all these negative impacts.
Right. And how that's found in nature, right? It's just like things repairing itself and getting tougher and not being like brittle and catastrophic failure. So I really found that part fascinating too. And I thought also just the incorporation of additive manufacturing to reduce waste by as much as possible was really interesting, as well as like the hockey application. So we saw how this helicoid structure is often compared to carbon fiber used in similar applications. So stick around to learn more about the various applications of this structure. And even I think Lorenzo had really good advice at the end, which is worth tuning into. So yeah, let's get right into the episode.
Hey everyone, we are excited to welcome today's guest, Dr. Lorenzo Mencattelli, Director of Research and Development at Helicoid Industries. Lorenzo is an expert in composite innovation and R&D project management with extensive experience in enabling research engagement between industry and academia. While obtaining his PhD at Imperial College London, thank you for joining us today, Lorenzo.
Thank you for having me here today.
Cool. So before we kind of dive into the helicoid technology, let's first discuss how you ended up at this company, Helicoid Industries. So the traditional route is, applying online, networking, and applying for a job. But Helicoid Industries actually reached out to you with an opportunity, which is very unique. So how did that job opportunity come to fruition?
Yes, exactly. That's quite a nice story, actually. So as you know, I've been doing my PhD on bio-inspired microstructures and looking at way of improving advanced composite materials. And part of this work was focusing, in fact, on helicoid technology, which is the core technology of Helicoid Industries. And so I've published journals. My name was out there, ready for the industry to be picked up. And make a good use of the technology. But the technology itself has been known and researched by many universities and groups all around the globe. And basically, the former president of Helicoid Industries was also a former executive manager of a company that I used to collaborate with during my PhD. So they got to know about this piece of research being done at Imperial College London. So they engaged with us, and at the beginning we did some consultancy job for Helicoid Industries, and eventually the challenge of commercializing bio-inspired technology. It's quite exciting. It's something quite new to the composite industry. So I decided to join and take part to this adventure.
That's awesome. So what got you passionate about this space as a whole, like bio-inspired technology and helicoid structures specifically?
So it's the way we approach as engineer or material scientist, the composite materials in a completely different way, kind of leaving behind the common rhetoric and way of the designing composite structure, which is mainly looking at designing for stiffness and strength, and rather looking at what you can do beyond designing the structures and actually designing the material itself, and the way you architect the microstructure of the material to improve performance of these materials. And biomimicry is a very effective tool to do that. So that's what excited me about looking at biomimicry and composite materials.
And so that's great background around like how you got into the space. But now maybe can we dive into what a helicoid structure is and where you can actually find it in nature?
Yes. So helicoid type of microstructure is actually one of the most abundant microstructure that you can find in nature. You can find it in several wood type of architectures, as well as in several exoskeletons and protective equipment of crustaceans and other animals. For instance, we can find it in the lobster, in the scarabei cuticles, and also in the Mantis Shrimp, which is a kind of mascot of Helicoid Industries. Where the shrimp is actually one of the most aggressive animals in nature, and it uses its adductive club. So it's a club that it deploys to strike prey it feeds on, and the club reaches speeds equal to a bullet type of speed, and it manages to crack shells which are considered to be quite tough themselves. So basically, this club needs to be highly impact resistant, sustain multiple impact, and never incur into catastrophic failure. And if you look inside the club, what you will see is that in fact, this is a fiber reinforced composite. So it's composed by unidirectional layers of aligned fibers, which are slightly rotated one to respect to each other. So basically, you end up with this helicoidal type of layup sequence, where you have a very smooth transition in fiber orientation as you build up your laminated structure. And again, this is a type of microstructure that can be found in several different animals and organisms. And the way it's actually able to achieve very high impact performance is the way it's able to dissipate energy and activate specific failure mechanisms. So you know that in a fiber reinforced material, the load-bearing component, it's carried by the fibers, and the resin transfers that load across the fibers. So the ideal scenario in an impact event or in an event that could damage your composite is that you do not damage the fibers, and you rather dissipate energy through matrix failure. And this is exactly what this helicoidal architecture do. So basically, you have this highly tortuous and complex failure pattern where you tend to break matrix but leave fibers undamaged. And this allows you to dissipate huge amount of energy, but at the same time, preserve the structural integrity and load-bearing capability of the composite.
So I'm just looking at a picture of a helicoid structure right now, and it reminds me of like a spiral staircase. And so I guess my question then is like, how did you see that structure in nature? Like, what does that research look like? And then how are you able to connect the dots and be like, okay, we could use this in potential industry applications?
This is actually a key step in utilizing biomimicry, which is it should never be a copy-paste of what we observe in nature, but it's really all down to understanding the structure and function relationship for a specific feature in the biological microstructure, and then understand how you can get those principles, those relations, and apply them in engineering context. So in this case was what does a smoother change in fiber orientation provides compared to what is conventionally done in industry, which is using a very large interply angle, like plus minus 45, plus minus 60, and so on. And what you find out if you then apply your analytical tool, numerical tool, and the design tool that are used conventionally in industry, you will realize that you're able to reduce a lot the interlaminar stresses in your structure that are the major causes for the lamination damage, which is critical for composite materials. And you are able, once damage activates, to control that fracture and to steer it in this very complex and stable fracture pattern, which is a big jump, let's say, in performance that you do over conventional composite structures that tend to fail catastrophically, and you have complete lack of control over how damage in fact evolves and diffuse in these structures.
So as you're talking about like this stress evolution of like a fracture pattern that we know, it sounds like you're preferentially letting the matrix fracture before the fibers. And so maybe in practice and also in nature, are you able to repair the matrix? And then what would that look like if we can repair the matrix over and over again? Does the stress evolution change as we like try to build it back up?
That's exactly one of the inherent features of helicoid technology that we are trying to to exploit in industries. This self-healing capability, because indeed, if you're using a matrix that is reprocessable, like a thermoplastic matrix, or even an healing agent, right? So thermoplastic particles dispersed into a thermoset resin, then indeed you're able to completely recover the damage, because you're able to delay the occurrence of fiber failure, and hence you can recover damage. We have done trials at the at lab level for using carbon fiber materials as well as glass fiber material, and in fact we are able to recover properties and damage within the structure.
Can you then talk us through what like the processing of helicoid composites looks like? It seems like a complex structure, but I'm wondering what are the challenges and maybe the complexities that come with manufacturing these composites?
Yes. So let's say that this, as a historic period, this is a good time to deploy the technology in industry. And the reason is we have the help of additive manufacturing, for instance, that allows us to contain the cost of selecting several different fiber orientations instead of only a few. That could have been a challenge in the past, but it's no more a challenge. If you're looking at automated fiber placement or tape layering or tailor fiber placement, continuous printing of fiber reinforced composites. So there is a huge amount of technologies that enable a cost-effective implementation of helicoid technology into products. That is a challenge that we are able to overcome. Then the other challenge that kind of narrows down the range of applications where we can provide benefit is, of course, the number of layers that we have available to build up the helicoid structures. Because if you're looking at very thin composite structures that only uses 4 layers, that, of course, there is no room to get the benefit of helicoid structures unless you move to thinner materials, but that brings all kinds of cost increases associated with it. So it's usually not the optimal way forward. So the other limitation would be having enough layers available, which is around 10, depending on the application, to build up the helicoidal architecture.
And so now that we've kind of dived into what a helicoid structure is and the properties and benefits, now we can start talking about some applications. And so one application that is of my interest is in the battery industry. So could you explain how your technology could protect battery packs in electric vehicles and the benefits of using a helicoid structure versus another structure?
Yes, sure. So in electric vehicles, this is an area where, in fact, we are quite active, and we have a few developments in there. It's the underbody protection of the vehicle needs to meet 2 main requirements from the mechanical standpoint. The first one, it has to be stiff, so that if it receives an impact, the battery, the underbody doesn't deflect much to crash on the battery pack. But also needs to be impact resistant. So if you have an impact, it doesn't have to pierce through, right? For instance, an ideal material could be, for stiffness requirements, could be carbon fiber, right? But carbon fiber as a main big problem, which is brittleness. So impact performance actually would be very low. Hence, by applying helicoid, you would be able to maintain a very high strength and stiffness provided by the carbon fiber, but at the same time, you would be able to improve the impact performance. So that would allow you to end up with the underbody protection, which is safe, but also lighter, because by improving performance, you can decrease the overall weight of the underbody protection. If carbon fiber might be too expensive, especially for high volume applications, and you're using a glass fiber solution on the underbody of the battery pack, then we can also improve performance with glass fiber. Again, helicoid is a fiber architecture, right? So it doesn't depend, you can apply it on using different constituents, namely fiber and resin. So we can use it also with glass fiber material. And the last bit that maybe I want to touch base on is the possibility of introducing more sustainable materials into this high performance application. For instance, we are able to improve performance also of natural fiber composite, and that usually you would not use in a component as critical as the underbody protection of every battery pack. But by improving performance through helicoid, you would be able to make a more extensive use of this material, which decreases the overall carbon footprint and solution.
And so when we talk about battery packs, your helicoid seems like a really good protection solution. But another issue that battery packs undergo is that if for whatever reason that a battery does break and catches on fire, now battery manufacturers are starting to make like flame retardant parts of their battery pack. Could helicoids either have some sort of like fire resistant properties, or could additives be added into the matrix that could help these problems?
Yes, that's exactly. So you could add the additive in the matrix. You could use a matrix that is fireproof. You could use a protective barrier on the inner side of the battery pack that is the underbody protection that is fireproof. And you can actually integrate all sorts of multifunctionality on the underbody. If you want strain sensing, if you want some sort of conductivity, electrical conductivity, it's all bits that you can integrate because again, we are just orienting fibers differently. But you can use any type of fiber or coating on the fibers or additive to the matrix that you want to achieve specific multifunctional properties.
And so I know you already talked through the structure and the mechanism, but I was wondering if you could maybe dive into what that looks like in this specific application with the battery packs. So you mentioned the impact resistance, right? So can you just kind of like help me visualize what, like, if there is some sort of impact to these helicoid structures in an electric vehicle application, what does that mechanism look like?
So basically all the, that energy that is received by the underbody protection would be contained within the laminate, so the actual underbody part. So you wouldn't have any fiber splittering at the back side, which is the inner side of your underbody part that could damage the actual battery pack. You would prevent any high energy impactor to actually pierce through the laminate. While if you have a conventional lamination sequences, it's very likely that an impactor, with enough energy could pierce through that battery pack and then damage your batteries. The other thing is also on the other way around. Let's suppose you have a thermal runaway of the battery pack, which it's not necessarily related to a mechanical or impact event. And then what you want to do is to contain. They can be quite explosive, right? You know probably better than me. And what you want to do then is really contain that explosion or contain the fire and avoid and delay at least as much as possible that explosion propagates to the rest of the vehicle, right? So that is also something that would be improved by our architecture compared to a conventional architecture.
And so when we think of the helicoid structure, like Puneet said, it's like a spiral staircase. In the matrix, are all the helicoids aligned in the same direction? And so is it basically a one directional like impact resistance, or is there bidirectional, or is the helicoids all rotationally like random to the point where the impact toughness is the same in any direction that you hit it?
I would say that for an impact event, usually the most critical condition is an impact normal to the surface, right? If you have it at an angle, you have the critical component is the component perpendicular to the impact surface in a flat laminated structure, at least. Every design that we do is calibrated and performed against this worst case scenario. So if we are able to prove that, then all the rest should come as proven as well.
Are we implementing this structure like right now, or like how far are we away from seeing these structures, this technology in like an electric vehicle in the future?
So we are currently having an internal evaluation with a major tier one supplier for automotive. Hopefully everything goes well, and that would imply seeing it, I would say, in a matter of a year. So wow. that type of range. So
fast.
That's awesome. Yeah, congratulations. I'm saying we, but it's really you. So yeah, congratulations. And I guess then we can dive into another application then, which is like sporting goods. So, here in Minnesota, hockey is very popular. And so you've mentioned in a previous call, there's potential applications there. How could helicoid materials improve the performance of, say, like hockey equipment, like a hockey stick or maybe even a helmet?
Yes, it's a similar, if you want, scenario that you have for the EV underbody protection, in the sense that you want to have a structure that is highly tailored for stiffness, right, for playability purposes in this case. But at the same time, you want to guarantee that, especially ice hockey sticks, it's a very harsh sport, right? So players tend to break their sticks quite often. So you want to have a very good damage resistance and damage tolerance of those sticks. What we are looking at the moment is both at implementing it in the blade of the hockey sticks as well as in the shaft, and that is also two areas where we are doing advanced development, already performed in-field playability test to see how the technology responds.
And so we actually did another episode a while ago on sports innovation, and one example was that we made golf drivers out of single grain like metal, and so basically the frequency it transferred energy very efficiently, and so we were hitting the ball farther, and so it was banned. If we have more impact resistant, let's say sticks or other equipment, is that mainly just for protection and like longevity, or do you also see a performance increase now that it's a completely new type of material matrix?
So I would say that the big performance increase would be you are using, compared to a metallic structure, you're using a material which is way lighter, right? Mm-hmm. And that it doesn't necessarily mean that you need to make your golf shaft lighter overall, but it means that you can position the weight in a much more tailored way. So and customize that tool to that specific customer, or and make sure that you have much more freedom of design for that structure. While if you're using a big chunk of metal, right, that has to be in that specific location because that's where the driver face is, then you don't have the opportunity to balance out your shaft in a different way, right?
I just looked it up and I saw that hockey sticks like right now they're made of like layers of carbon fiber, and it seems to be a theme that maybe like very related product in these applications is carbon fiber. Do you see that in like continuing to be maybe like a competitor, or just like a comparison in for helicoid applications in the future, and how do they compare in terms of performance?
Yeah, so for sporting goods application, we are mostly doing developments using carbon fiber materials. So definitely that is basically what we do is to take a solution that is currently made with carbon fiber usually, and have a look at the reference layup that is currently being used in that application, and then we suggest an alternative helicoid layup that would potentially improve performance. So we are already working with mainly with carbon fiber in sporting goods, also some applications using glass fiber and natural fiber as well. And yes, we will continue to do so, I believe, for quite a while.
Nice. So what are like the main materials related challenges that your company or this industry maybe as a whole is facing? Is it like processing related? Is it more like just adoption of this new technology and being able to communicate its performance to investors or partners?
Yes, let's say that with the biomimicry and bioinspired solution in general, the main challenge is usually the cost and scalability of implementing the technology. So relatively easy to address that for sporting goods application, much more complex if you want to go to a high volume, highly cost sensitive industry, such as automotive, for instance. And in this context, actually, Helicoid is quite an exception, because most of the bioinspired material solution that you find around, they tend to develop in a hierarchical way from the nanoscale up to the macro scale. So if you really want to reproduce or the same benefit that you observe on the biological microstructure, you would need to be able to recreate that entire hierarchy, right? And that becomes a huge, almost impossible challenge even nowadays for scalability purposes. With Helicoid, we are already at the mesoscale, so the laminate level architecture. So let's say that we kind of jumped a bit the biggest obstacle, which is tailoring at the microstructure and the nano level. And that allows us to also address markets such as automotive, where we can therefore provide a solution that is cost competitive.
And so when you bring up cost, Helicoid's actually doing something else, and at least looking into it, where you would use additive manufacturing to make it more cost competitive. Could you go into how additive manufacturing could reduce the cost while maintaining these properties?
So additive manufacturing would reduce the cost in the sense that it would allow us to produce a helicoid component with virtually zero waste. That is the main cost improvement that it provides. And then what helicoid would do is trying to reduce the number of layers that you eventually use in your structure to decrease the structural weight. So eventually you have the cost advantage of zero scrap. You have the cost advantage of using less raw material overall because you are reducing the structural weight of your component. And you have the cost advantage also of increasing the rate of manufacturing because you are depositioning less material, so you are doing it faster, and which can increase the output of your machine.
And so I don't think laminates are specifically like a novel field. Like I believe there's lots of like manufacturing around it. So how would creating a laminate be different from doing additive manufacturing?
Historically, laminates were done by hand, and nowadays with additive manufacturing, it's just that instead of having somebody laying down the fibers, you have a machine, right? A robotic arm, basically, just placing down the fibers. Then, depending on the specific applications you might and the raw material you start with, whether it is a pre-impregnated material that has already the resin in it, or whether it is a dry fibers, whether you are building up an axisymmetric component, then you have all different types of additive manufacturing related to fiber reinforced composites.
And then I've actually had some experience with laminate material. And so common issues arise around basically manufacturing quality and embedded stresses, such as not letting it thermally relax and other just internal stresses in like the polymer matrix. With additive manufacturing, does that resolve some of these issues as now you're being very deliberate in how you apply your matrix? Or how are these challenges like overcome in this new method of manufacturing?
I wouldn't say you are able to resolve the problem in the sense that with additive manufacturing, and there is a huge amount of research both done at industry and academic level in this area to trying to characterize the manufacturing defects that are generated during additive manufacturing for fiber reinforced composites, and kind of create a link between processing parameters that you use to program your machine and the defect that you get at the end in your structure to be able to control those. So that is definitely something that you are not solving with additive manufacturing. In some cases, you are making it worse, actually, in the sense that imagine that you need to cover up a certain area. And if you do it by hand layup and cutting materials from a very big roll, you just cut a uniform sheet of material that it covers completely that area. With additive manufacturing, you will have to lay down in smaller pieces materials. And when you go to one strip to the next one, you might have some overlaps, you might leave some gaps between the strips, and all those are sort of defects that you introduce in the structure. So in those cases, you would make them worse.
That's fascinating. So you mentioned that Helicoid Industries is now at like the mesoscale. Can you talk through what were your biggest learnings going from, that very small scale nanoscale up to where you are at now?
The biggest learning and also challenge is trying to understand how we can actually take everything that you can learn from the natural microstructure, embed in that learning also the engineering constraints that you find in actual product, because those constraints often rule out most of your design space, and you are only able to work in a very constrained design space, which is good because it stimulates also problem solving and innovations on how to further develop the technology, which is basically what has led us to increase the IP portfolio of the company from where it started, which was, the pure staircase, constant step helicoid layup. But when you start putting in all these engineering constraints, then you realize that microstructure is almost impossible. So you start thinking how then you can improve still an actual product by using the same type of knowledge and learning. And I think that's the most interesting and fascinating challenge so far.
That kind of leads into something that you discussed in a previous call, which sounded crazy, but you're able to use biomimicry to potentially exploit pre-existing damage in materials to actually make them tougher and stronger. So can you explain how in nature materials have accomplished this, and maybe how in an engineering application that could be achieved?
Yeah, so this is it's quite interesting, because as human and engineers, we tend to a different type of perfection than what nature tends to. And for us, perfection is trying to make everything as homogeneous as possible. If you have a fiber reinforced composite, you want the fiber to be as straight as possible, with no misalignment, with no porosity, no defect whatsoever. And this is what we do. And by doing that, what you create is you increase stiffness and strength, but you are really also embrittle your materials, and you make them very prone to damage. In nature, you try to do something in a different way, because nature has to work with very cheap and low performance constituent, and hence you find in nature that structures are not symmetric. You find there is a lot of porosity. And you also realize by investigating this microstructure that all these defects actually helps with activating some of the failure mechanisms that I've discussed earlier during the call to achieve this performance improvement. For instance, one typical example is the cortical bone or bamboo microstructure, which are very similar in the sense that they are formed by bundles of fibers that developed at different hierarchical levels. And by insert, so there is a weak link in this microstructure, which is the interface between the bundle of fibers and the surrounding material. And what happens when you pull these structures in tension is that you activate that link. So before reaching the fiber failure, the weak link fails, and which means that these bundles debond and creates a very large surface area where they can then be pulled out and dissipate a huge amount of energy during that pull-out process. And this allows to have a very stable load increase rather than a very sharp drop once you reach the failure load for the fiber themselves. And this in industry, it's been kind of accepted with metals, because back in the days, if you had a crack in your cylinder of your engine, what you would do is just drill a hole at the tip of the crack to blunt that crack tip. That would stop the crack. And you are introducing a defect, right, to create a crack stopper. And this will have to come back at some point, especially if we look at, for instance, a blossoming market like urban air mobility, where you have this small aircraft that needs to be certified for flight, but at the same time, they need to cost as much as a car. So that you have a big challenge, and to achieve the high rate manufacturing and cost to produce these vehicles, these aircraft, because they are aircraft manufacturers, they would want to create structures that are as much integrated as possible in basically just one piece, right? While at the moment you have a lot of sub-assemblies and pieces that you put together in assembly to deliver the structure. So the problem then becomes, what if you have a damage in this one piece structure? You don't have anything to stop that. While if you have an assembly, you have a damage in a panel of your wing, the damage reaches the edge of the panel, the crack would stop. So at this point, then having biomimicry to help us with designing the materials to create a crack stopper, crack arrest mechanisms, really would help to deliver indeed and allows these structures to be produced and fly.
That's very interesting. I know that a lot of companies are, like you're saying, moving to additive manufacturing, or even more advanced casting methods to reduce the complexity of parts. And so I never thought about that issue, is that, if I need to replace a part of my car now, I have to replace half the car. And so I can see where this can be very important in the near future.
Yeah.
Well, we have discussed a lot today about biomimicry, helicoid structures, and composite materials. If you had one final piece of advice for engineers who want to learn more about biomimicry and apply it to solve problems, what would it be?
I would say, first of all, trying to be very curious about it and try to dive into the biological aspect of it. Ideally, you would always want to have an opinion from a biologist when you try to apply biomimicry to a concept. The piece of advice that for me was really important is biomimicry can lend itself very easily to just being a marketing story, because it's exciting, it's cool. You don't want to do that, because otherwise the idea itself would lose credibility over time. So it's really trying to use it as an extra toolbox to help you solve your problem without using solutions that are offered off the shelves, which is usually what engineers, including myself, tends to do to solve their problem. So it's trying to think things differently.
What advice, because it's very common in industry and other places for people to find a cool application. And so, for example, find a cool biological system and try to create a actual product before a problem arises. Like you said, making sure that it's one of the last things to bring out the toolbox. How can you, through your experience, give us any advice on how to know when to bring in new techniques and new things where you're not forcing it beyond what we already have?
One good support, well, first of all, having increasing awareness on the biomimicry and the fact that there is a tool there that can be used to help you with solving your problem is really important. The other important aspect for people who are not yet into the subject, into the field, is to have a sort of database of solutions that are already out there to have access to and stimulate your creativity. And likely we have a cluster that collects bio-inspired solutions for different industries, not just materials or composite, but also for architecture, medical devices, and so on. One in the US is the Biomimicry Institute. In the UK, there is Biomimicry UK and Innovation Lab. And referring to these institutions would really help to connect with the network of experts and right people to refer to in case you want to have a project that implements biomimicry to solve your problems.
I love that. Yeah, it shows the importance of leveraging others' expertise to kind of push the frontiers of research. But yeah, this was a wonderful episode. Thank you so much, Lorenzo, for joining us today. That was very interesting to learn about the helicoid structure and its potential applications.
Yeah, it was great for me too. Thank you for the invitation.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.